Welcome to solverfy.
In this problem, we have a pulley system driven by motors D and C pulling blocks B and A. We're given the accelerations caused by motors C and D. C's acceleration is defined by 3t squared meters per second squared, and D's acceleration is constant at 5 meters per second squared. The system is initially at rest, and what we're interested in finding is when the distance between the edge of blocks B and A, which we're calling D here, is 0. And we're given that this is initially 3. So we'll go and find that. I've gone ahead and defined some fixed points in this system. So one coordinate I'm using is this DBC, or this DB, which is the distance between B and the initial edge of block A. And I've defined AW, which is the distance between A's pulley here and the wall, and AC, which is the distance between A and the motor C. So what we're interested in finding then is when D is equal to 0. And this will occur when the change in dB plus the change in AC or AW, doesn't really matter since these are going to be the same, is equal to our initial distance there. So once the change of both of these blocks added up is equal to our initial distance, then the distance between them will be 0. So to start with, we can begin by defining some equations for each of these deltas. So delta dB is pretty simple since it's just a block connected to a motor that's pulling its string. It's just going to be the equation for constant acceleration motion since it's constantly accelerating. So that's just V naught T plus 1/2 AT squared. And we know that V naught is 0 since the system is initially at rest, so we can discard that term. And we'll find that if we plug in A here, this is just 5/2 T squared. Now for delta AC, this one's a little trickier. We'll begin by defining the changes, the instantaneous changes, the time derivatives in AC, AW, and L. We know that the time derivative of L must be equal to negative of this. And we know that the time derivative of L must also be equal to the sum of the time derivatives of AW and AC. We also know that since AW and AC are on a taut string connected by a pulley, that their time derivatives must equal each other. So since we were defining this in terms of AC up here, we can go ahead and substitute in AW for AC here to get that L dot must just be 2 AC dot. Now that we have that, we can plug in our equation for L dot here that we defined as minus 3 T squared. Excuse me, this should be L double dot because this is the acceleration. So before we get L dot, we should before we actually get L dot, we should figure out what that is. So L dot is just going to be the integral of L double dot with respect to time, which if we take the integral of minus 3 T squared with respect to time, this is just going to be negative T cubed, and then plus some constant for the initial velocity. but we know that the system is initially at rest, so this is 0. So we have L dot, and it's just minus t cubed, and so therefore AC dot is just minus 1/2 t cubed. Now, we have this time derivative, and so to get the change in AC, we'll just integrate this again. And since we only care about the magnitude of this change, we can take an absolute value here and just cancel out that negative. So this integral, we're going to change this t cubed to a t to the fourth. So this is going to be t to the fourth, and we need to drop a 1/4 in this whole thing then to balance that out. So that'll give us 1/8 t to the fourth. And this we don't have to add a constant to this because we're just interested in the change of this. We're not interested in the actual value. So now that we have everything, we can go ahead and plug it all into our equation. And we'll get that this is 5/2 t squared plus 1/8 t to the fourth is equal to d naught. Now, if you notice here, we're pretty close to a quadratic equation if we shuffle our terms around. So we can get 1/8 t to the fourth plus 5/2 t squared minus d naught equals 0. And if we wanted to solve for t here, we could just use your preferred way of solving quadratic equations. I'm going to use the quadratic formula since I think that's the most expedient for this problem. So we'll have minus 5/2 for b plus or minus the square root of b squared minus 4a is 1/8, c is negative d naught. So that's just d naught, and we'll take that negative out here to make this a positive. That's all over 2/8. And t squared is equal to this. So we can simplify this a bit. 2/8 is really just 1/4. 1/1/4 is really just 4. And we can put the 4 here, and we can put the 4 here such that we can rewrite this all without a nasty denominator as minus 5 times 2 since we're canceling one of these 2's. So that's minus 10 plus or minus 4 square root 5/2 squared plus 4/8 d naught. Why don't we go ahead and actually multiply out this square to give us 5 squared over 4. We can pull out another 2 from this square root here. If we pull out a 4 here, so we pull out the 1/4, and then it goes to the square root and becomes 1/2, and then it divides into this 4 here. So we get 2 square root 5 squared plus 4, and then we pull out a 1/4 here, so this is 4/2, so that's 2d naught. And this is about as simplified as our equation can get without plugging things in. And if you notice, this equation can also be rewritten as 2 times the quantity minus a d plus or minus square root ad squared plus 2d naught. And if we look at some of the limits of this system, we don't care about the negative on this because we're not interested in what happens in negative time. We only care about the positive time. At the limit where d naught, the initial distance, were to be 0, then this would be instantaneous because the square root would cancel here, and then these two would cancel, so that would be 0. If AD is very big with respect to d naught, then a similar thing would happen because the square root would approximately just be AD again. And if d naught is very big, then of course it'll take longer. So we have a good-looking solution. That's again equal to t squared. So we can plug things in again. So 2 minus 5 plus square root 25 plus 2 times d naught, which is 3. And if we multiply that all out, 2 minus 10 plus 2 square root 25 plus 2 times 3 is 25 plus 6, which is 31. And we can look in our calculator to get a value for that. So 2 times square root of 31 minus 10, and that's about 1.14. And t is just the square root of that. So t is the square root of that, and that is about 1.07 seconds. Now, that was the first part of this problem. The second part asks us to find what are the velocities of the blocks at this time. These are pretty easy for the blocks now, since we had to find the velocities in order to get the equations for the change in the distances, and we can just plug in time. For block B, this is just going to be a dt, since the block B is connected to D here. It's just the constant acceleration equation. So this is just going to be 5 times 1.07, which is just 5.35 meters per second. For block A, the equation, if you'll recall, was a little more complicated. It was 1/2 t cubed. So this is going to be 1/2 t cubed for block A. So that's going to be 1/2 times 1.07 cubed, which is 0.5 times 1.87 to the power of 3 is 0.613 meters per second. This is B, A, and time. And those are our solutions.